Good day everyone. So we are Barbie girls. Today we're going to talk about normal density and discrimination function topic. So here a quick overview of what we're going to discuss today. Firstly is the introduction, followed by zero-one loss function, normal density function and discrimination function. For all the concepts that we discuss here are based on Duda, Hart and Stock pattern classification textbook. We continue with the introduction. So the objective is to focus on how normal density function are used in classification problems and how discrimination function help us make optimal decision. For this topic, Bayesian decision theory play a role to provide a probabilistic framework for the decision making by focusing on three components, which is class probabilities, class conditional, and also the decision rule. We assume that the data follows a normal distribution, so it allows us to model class conditional density more easily using mathematical formulas. So once we have this probability, we can apply discrimination function that help us determine which class a new input most likely belongs to. So in short, this function evaluates the input X and compare it across different class models to find the best match that can help us make the most accurate decision.
This slide explains the zero-one loss function, which is commonly used in classification problems. The zero-one loss function is very simple, where it gives a total loss of 1 if the prediction is incorrect and a total loss of 0 if the prediction is correct. The decision rule for this formula is very simple, where we choose the class with the higher posterior probability to avoid the chances of being incorrect. This formula here shows how we calculate the expected risk, or known as conditional risk, of choosing a class omega I. The formula sums up the probability of all the other classes, which gives us the chance of misclassification if we choose omega I class. Since the total probability equals to 1, we can simplify the formula of expected risk as 1 minus the posterior probability. So, the higher the posterior probability, the lower the risk. This is why we choose the class with the higher posterior probability.
Next, let's proceed to discuss the concept of normal density functions, where in this case, we have two types of normal density, which are univariate density and multivariate density. Let's focus on the univariate normal distribution on the left first. A univariate distribution only involves just a single random variable, such as height, test scores, and errors measurement. The univariate density is completely defined by two parameters, which are the mean and the variance. The mean determines the center of the distribution, while the variance determines the spread out of the data. Here is a bell-shaped curve that represents the normal distribution. The highest point is at the mean, and the curve is symmetric around this point. Hence, we may use the expression of the notation, which indicates that X is normally distributed with mean and variance. On the right side, we have the multivariate normal distribution, which involves two or more random variables at the same time. For example, we can analyze both height and weight simultaneously. In the multivariate case, each of the variables has its own mean and variance. Hence, the strength of the correlation between variables are very important here. The notation indicates that vector X is distributed as multivariate normal with mean vector and variance covariance matrix. The covariance matrix not only captures the variance of each individual variable, but also how they covary with each other.
Moving on to discriminant function, it is used in pattern classification to determine the class of an input based on its feature. In multi-class classification, the decision rule assigns input X to the class W sub I if the discriminant function G sub I of X is greater than G sub J of X for all J not equals to I. In other words, class with the highest GX score is selected. In the minimum error rate case, the discriminant function chooses the class with the highest posterior probability, which is the class that is most likely given by the input X. There are three cases based on the covariance assumptions. Case 1 is when all features have the same variance and no correlation. The decision boundary is linear discriminant and has a spherical clusters. Case 2 shows that when covariants are shared by arbitrary, which allows discriminants with elliptical clusters. The third case is used when each class has its own covariants, leading to quadratic discriminants and flexible curves decision boundary.